let's talk here cyclic ethers. We already made one a minute ago, and I also told you cyclic ethers are common solvents. So here's tetrahydrofuran, here's 1,4-dioxane, a little higher boiling solvent that's used sometimes. They're very common with anionic reactions. So if we've got a Grignard reagent or a lithium reagent or something like that, an ether solvent will typically work well. They're incompatible with strong acids like we've showed before. That will cleave the ether and break the ring open. And just like we did before, we can make them by an intramolecular Williamson ether synthesis. I showed you one with a Grignard reaction, but we can do one, that's not even nearly as fancy. I can do this 1, 2, 3, 4. So 4-bromo, 1-butanol. Here, I'll even put a couple of methyl groups on there. There. Let's put an ethyl on number 2 and a methyl on number 3, just for fun. So what I can do to make this into a cyclic ether, sodium hydride to deprotonate the alcohol. Oops. O minus. Then what will happen spontaneously is the intramolecular Williamson ether synthesis, where the O minus will attack the carbon that has the leaving group attached. Remember, I said it's helpful to number what's going to be part of the ring. The oxygen now will be part of the ring. So I'm going to have a 5-membered ring. So it's going to look like THF, but because of the things I had attached, it's going to be a little different. I'm going to have now an ethyl group on carbon 3, a methyl group on carbon 4. So that numbering is a good way of keeping track of what's going to be where when the ring closes. So the ethers that are, 5, 6, 7, 8-membered rings, things like that, react pretty much the same as open chain ethers. Okay? Epoxides are much, much different. An epoxide is a 3-membered cyclic ether, so an O and 2 other carbons in a 3-membered ring. And there's tremendous ring strain, right? The bond angle is, somewhere around 60 degrees where it would normally be 109 degrees. So a tremendously strained bond that makes them very high in energy, very reactive, because there'll be a tremendous driving force to relieve that ring strain. So here's ethylene, CH2, double bond CH2. It can be industrially oxidized to make an epoxide, which is called ethylene oxide. That's how common names for epoxides work. It's the alkene and oxide. Okay? The IUPAC name is 1,2-epoxy ethane. So use 2 numbers in there to show where the O is attached. So 1,2-epoxy ethane. Okay? The common name talks about where it came from. The IUPAC name is what the actual compound is. Right? We've already seen how epoxides are formed, usually with a peroxy acid. So RCO3H looks like this. RC double bond O, then 2 adjacent O's with an H. That's a peroxy acid. Okay. And MCPBA, metachloro, right? Here's a chlorine meta on this ring to peroxybenzoic acid, right? Regular benzoic acid would be COOH. This is peroxybenzoic acid with the 2 O's in there, right? So what that does is, here's our starting material, just an alkene. It places an epoxide over the 2 carbons of the alkene. Just in case you're interested in this mechanism, this is not something that you need to reproduce, but sometimes it's helpful in remembering how the reaction goes. It's a concerted cycloaddition, so this happens all at once, right? And that means the geometry of the double bond will be retained. So, it's kind of hard not to in a ring like this, but even if it's an open chain, the geometry will be retained. So let's just make a trans double bond, something like that. Okay? So if I've got that, and I've got a peroxy acid, I'm going to draw it very carefully here with just the O next to the H close to the double bond. C double bond O, and then there's R like that. So the cycloaddition works like this, where the carbonyl double bond attacks the hydrogen itself of the peroxy acid, and that pushes 2 electrons towards 1 carbon. The electrons of the double bond will attack the oxygen itself. That breaks the OO bond, which becomes the new C double bond O. So see if you can follow that. Right? There's our epoxide, and then plus the other one is the C double bond O. That one is COH, and that's R. So they've done studies with radioisotope labeling of the 3 oxygens in that peroxy acid, and they found that the one next to the H is the one that's incorporated into the epoxide. Okay? Of the peroxy ones, the one closer to the C ends up being the new carbonyl. The old carbonyl is the new OH that way, just because of that really interesting cycloaddition. So I will not ask you to recreate that mechanism, but sometimes it's helpful for envisioning the product. I mean, no chance for the double bond to isomerize. That O just gets delivered to one face of the double bond, and that's it. If I have a halohydrin, right, that's where I add halogen across the double bond, and the intermediate there is in this case, a chloronium ion, a 3-membered positively charged ring, which gets opened by water. Okay? That's why the stereochemistry is such as it is here. The OH is on one side, the chlorine is on the other side. That's always what happens when a 3-membered ring is opened like that. It's essentially SN2 coming from behind it that way. But then, if I have this, here, let's just say H2O. If I have this halohydrin, that's this, which is where I have a halogen and an OH next to it in the molecule, or in the same part of the molecule, deprotonate it with some sort of base. Okay? We have an intramolecular Williamson ether synthesis. So the O minus just sort of, it doesn't really even go to attack. It just kind of leans over right there and ejects the chlorine from the other way, right? So 2 methods to make an epoxide out of an alkene. Both have the same stereochemistry. There's really, I guess, not much advantage to one over the other, but right. So, but in both cases, they'll get you a epoxide. We could do it with MCPBA. Or we could do it in 2 steps. I guess the peroxy acid method is probably preferred since it's just 1 step, but it makes a good mechanistic step for us to understand the other way. Step 1, make the halohydrin. Step 2, deprotonate it. Both of those reactions will make an epoxide, right?